recording is on for the second half here. Any questions about what we were up to in the first half? By the way, I didn't answer the question about why it's like bowling. I guess maybe it wasn't a question. Why is it like bowling here? I think, and you can correct me if I'm wrong, like if I counted who was vertex number 1 connected to, maybe I start up here. Vertex number 1, if I look at its handshakes, they go to 2, 3, 4, and 5. So I could say, okay, in the bottom row, I'll put vertex 1 is connected with 2, 3, 4, and 5. And then in the next row, I look at who is 2 connected to that I haven't already accounted for. So 2, 3, 2, 4, 2, 5. So 2 is connected to the larger numbers, 3, 4, 5. I could stack them up like bowling pins here. 3, 4, and 5. Maybe I should even put these 2, 3, 4, 5, 3, 4, 5. And you keep doing it like this. If I take 3 and I look at, if I take 3 and look at who are the larger things that it's doing handshakes with, and it's just 4 and 5. And then finally, if I look at 4 and ask who are the larger numbers that it's handshaking with, it's just 5. Is that what you meant for it looking like bowling or being related to bowling? I wasn't sure. Anyway, here's a stack of 5 choose 2, excuse me, 5 times 4 divided by 2, which is the same as this 10 here, the 10 bowling pins. Okay, I'm going to assume that's what you meant. So what I was going to tell you about was starting in on some of the graph theory from chapter 7. So what I want to do is, first of all, talk about what's informally a graph. So the definition won't be excessively formal, but got to define these things at some point. And this is what's called, what I'm defining is a simple graph. I'll talk later in the class about what are non-simple graphs. But a simple graph, usually people write G for the name of the graph, and it's got 2 things. It's a pair of the vertex set, vertices, which is a set, and edges, which is another set of pairs of vertices. Certain unordered pairs of vertices. V, okay. And so I'm going to write this, but I will do an example in a second. It's a set of vertices V and a set of pairs E, the edges of vertices. And most of the time, what I'm going to do is be incredibly informal and draw them as pictures, because here's an example. Oops, that's supposed to say e.g. example. Let me put vertex number 1 here, and vertex number 2 here, and vertex 3 here, and 4 here, and 5 here, and 6 here, and 7 here, 8 here. And I'm going to draw edges, which are like those handshakes between some of them. So imagine like some of these people are friends, and some of them are not. And I only put edges between the ones that are friends. So this edge from 1 to 5 is just, I was drawing it going underneath the edge from 3 to 4, but that's not important whether it goes under or over. The only real thing that's going on here is that I've got a graph with a vertex set V, an edge set E. The vertex set V, that's an equal sign. I hope I'm not confusing people. That's just a big equals and it's going down diagonally. And I'm saying the set V is equal to the set 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's my set of vertices. And then the edge set here is a whole bunch of these unordered pairs, 1, 2, 2, 3, 1, 5. So it's the pairs where you see an edge there. And so I'll start writing 1, 2, 2, 3, 3, 5. But then I'm going to get tired of writing all those curly braces. So I'm just going to start writing 3, 4, because there's an edge from 3 to 4. Who else do I have? 1, 5, 5, 6, 6, 7, and 7, 8. So let's put some commas. And let me close the big set brace that corresponds to this one. Whoa, didn't mean to do that. Okay, does everybody understand what the vertex set is and the edge set is, V and E here? And so it doesn't matter how I draw it. I could have drawn this same graph differently on the page, but it still represents the same graph. Okay.
Do they have to be unordered? Like, do they have to be unordered pairs, or can you have them directed too?
Later, we'll talk about directed graphs. For the moment, this is a simple undirected graph. And let me just say what simple means. The simple part is not so much about the lack of direction, the fact that it's undirected. Simple says that I'm not going to allow something that, let me temporarily draw something that I won't allow. When we do multigraphs, we'll let ourselves do that stuff like that and have multiple edges between the same pair of vertices, 1 and 2. I'm not allowing that for the moment in my simple graph, but it's not so important. I could have allowed it. It's just, I'm not. Okay. Another thing, by the way, that would be allowed in certain kinds of multigraphs would be loops, to have edges that start at vertex 3 and end at vertex 3, so they don't really have two endpoints. I'm not allowing that for the moment. Okay. Other questions? These are good questions. When people talk about graphs, they always have to be clear about which kinds of graphs they mean. Simple, multigraphs, loops, no loops. No. All right. So what is this going to have to do with anything we were talking about before? I want to actually talk about the degrees, the vertex degrees in a graph. So this is more just general graph terminology. Each vertex, little v and capital V, has what's called its valence or its vertex degree. I'll write, and I'll write it like this: deg within G of the vertex V. And it's sometimes, another word for this is valence, particularly people who do chemistry. When you think of the vertices as being like atoms and the edges as being chemical bonds to other atoms, they talk about the valence of a vertex. The degree is defined to be just the number of vertices. Whoops, I missed a cardinality. Okay, so it's the cardinality of a certain set. It's the number of other vertices, W in V, such that you have an edge from V to W. So the pair V and W is in E. Okay, so let me make that thing colored and actually write down some of these valences, these vertex degrees here. So I'm going to label each of the vertices here in pink. Maybe I'll even circle it. No, I'll do it in pink since we've got the color, with its degree. So I look at vertex number 1, and I just check how many edges are coming out of it, and I see 3 edges coming out of it. So that thing's getting a pink 3 for its vertex degree. Degree of 1 is 3. Let me write that. Degree within G of vertex 1 is the number 3. Okay, and 4 has 3 edges coming out of it, so 4 also has degree 3. 5 has degree 3. Let's see, somebody doesn't have degree 3. Vertex 3 has degree 2. Vertex 2 has degree 2. Vertex 6 has degree 3. Vertex 7 has degree 1. And vertex 8 has degree 1. So I've labeled the degrees of every vertex, these pink numbers. Everybody good? Questions? All right. And so if we total them up, that's the total of the vertex degrees. What do we get? We get, let's see, a 1 occurs, a 1 occurs here and here. So we got 1 plus 1. We've got a couple of 2s, and then we got 4 3s. So let me write that down. 1 plus a 1, a 2 and a 2, 3, 3, 3, 3. And that totals up to, let's see, 2 plus 2 plus 2 is 6 plus 2, 18. Everybody agree that the sum of the vertex degrees was 18? All right. And what does this have to do with the previous thing that we were doing? Well, in these examples, right, I was drawing some graphs back here. And if I label these graphs, yeah, that's right. So let's hold on to that thought. If I label these by their vertex degrees, let me do that. I'm gonna put the vertex degree for that one is 0. It's not connected to anybody. These both have vertex degree 1. Here everybody has vertex degree 2. Here everybody has vertex degree 3. And in this one, everybody has vertex degree 4. And so if I was to put in the sum of the vertex degrees, then I'm going to get 0. 1 plus 1 is 2. Here I'm getting the 2 plus 2 plus 2 is 6. Here I'm getting 4 times is 12. And here I'm getting 5 times is 20. Okay. And you can see these numbers that I've written, this sum of the vertex degrees is actually twice that number of handshakes that we were counting before, which was the number of edges. And so that's actually the point. This thing, this 18 here, is also twice something else, and it is the number of edges. Let me count the edges here. 1, 2, 3, 4, 5, 6, 7. Whoops, I failed. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think there are 9 edges. Okay, so let's understand why that's true. This is something you'll find in the book. This is proposition 712. So in that section 7.1 that starts talking about vertex degrees. In any graph, G with vertex set V, edge set E, if we sum over the vertices in capital V, the degree, so the sum of the vertex degrees, that's what we were counting when we summed up those numbers in pink. The claim is we're always going to get 2 times the number of edges. It's always going to be an even number. And it's going to be 2 times the number of edges. Let me ask people something. This summation, oh, Matthew, you're asking, are the vertices typically labeled with numbers? Seems to make more sense to use letters. Yeah, you know, you can label vertices with whatever you like. And you're right that in this situation, because I've been labeling them with pink numbers, which are the valences or the degrees, it's funny that I also had numerical names for the vertices, but I'll be free to, you know, call the vertices whatever I like. Sometimes I'll call them V1, V2, V3, you know. But this is something I want to check in with people to make sure they're okay with. You're probably much more used to summations that always look like, you know, a summation as I goes from, you know, 10 to 20 of some function of I, you know, something that goes in here. But are people used to the idea you can have summations over any set and have something that's your summand inside that it just depends upon that thing, the little v in the set? Is everybody okay with this notation? All right. If that confused you, let's talk about it in office hour a little bit and make sure that the notation isn't a difficulty. It's just that we're going to want to do this kind of very flexible summations all the time. It's extremely useful in thinking about stuff. I'm going to take this away. All right. And so let's think about why is this proposition 2? And let me remind you, I was saying that it is in the book, you'll find this as theorem 712. I think it's on page 130 in the book. They talk about that, this proposition. All right, so let's prove it. I don't think we've done many proofs yet so far where we actually wrote the word proof, but let's do it. And one way to do this is one of these situations where it makes more sense, rather than calling it Shepard's principle, I'm going to call it the counting in two ways. So what I want to do is count the set of half edges. So that's my set B, right, in two ways. So let me draw that graph from the previous page. Let me redraw it here. Take it, actually we can take it with the colors. It doesn't matter if we've got the vertex labeling. Let me repaste it here. And so what I want to do is think about those half edges, right? So remember how the half edges look? They look like this. Okay, so everybody remember what I was saying about half edges and why these would be the half edges in this graph? And so what I want to do is think about counting that set, right, in two ways. So every edge E, say with vertices I and J, every one of those things in our set of edges, capital E, it contributes to two, whoops, two, I have to write the word, two half edges. And when I've got a vertex, let me call the edge E, and here's vertex I, and here's vertex J, it contributes to that half edge and that half edge. On the other hand, so in that sense, the number of half edges, let me say this explicitly. So B, the set of half edges, right? That's a set that I'm going to count in two ways. It should have size 2 times the number of edges. Does everybody see what I'm saying there? Questions? Okay, but on the other hand, also every vertex, V and V, little v and capital V, contributes its degree, right? If you've got a vertex and it's got 3 edges in the graph coming out of it, then it's got 3 half edges that it contributes to B. When I say elements, I mean half edges. Do we agree? So just to make sure, right? This vertex number 1 contributes these 3 half edges. Vertex 2 contributes, oh, I forgot to color some of them. Excuse me. Vertex 2 contributes these 2 half edges coming out, right? So it's whatever its degree is, that's how many contributes. And so the conclusion is that, where are we? If I want to count up B, I could think of summing over all the vertices and summing up how many half edges did that vertex contribute? How many emanate from vertex V, little v? Okay. So what did we conclude? The cardinality of B is equal to 2 different things, right? Cardinality of B is equal to 2 times E. Cardinality of B is equal to the sum over the vertices of the degree of G. And so the sum over the vertices of degree of the vertex is 2 times cardinality of B. They're both equal to B, cardinality of B, the number of half edges. Everybody okay? All right. Here's an end of proof symbol, end of proof. That's like QED. So when you see me write that, that means I think I've proven it, but you might think, no, he hasn't. I'm not convinced, you know, or I just didn't get it. So stop me when I think I've proven it. That doesn't necessarily mean we've proven it. In fact, I might just be wrong. Maybe I haven't proven it. Everybody okay? All right. Let's get a corollary or two. Here's one that people often state. So if you have a party and there's an odd number of guests, there's always going to be somebody who knows an even number of other guests. Strange phrasing. It's like a weird way to describe a graph. It's the graph of who knows whom. A party with an odd number of guests. Some guest has to know an even number of other guests. Okay, so why is this a correlate? Let me first of all phrase it as a graph thing, not trying to disguise it. What if some relations are, parasocial, so there's some kind of directed thing? I don't know. This is not a psychology class. I didn't even know the word parasocial, so thank you for educating me. No, we're not going to count those right now. Mark is correct. Good. But what am I doing here with this, you know, knowing and not knowing? As I said, this is really a graph thing. Suppose we've got a graph, VE. This is going to be a simple graph, and it's not directed, and yes, no parasocial, nothing. What are we saying? The vertices in the graph are the people at the party. So capital V is the people. Edges between people who know each other. Undirected. And so has V, if it has, let's make this grammatical. If the cardinality of V is odd, then some vertex has even degree. That's the graphy way of saying it. All right, so let's see why this is true. Let's prove it from the previous thing. Well, you know, there's different ways to think about how to prove this. If anybody'd like to try and explain it, then feel free. We'll work with it. Anybody wants to give it a go?
Oh, I think I have it.
Okay, give it a go.
So you have an even number. Okay, so we have the sum of all of the degrees is two times the cardinality of the edge set. So it's an even number basically.
Yep.
And it's, so let's just suppose that everyone, let's do this by contradiction, I guess. Let's suppose that everyone knows an odd number of people. Then you're summing an odd number of odd numbers, which will be odd, not even. And there's a contradiction, so it has to be even.
Yeah, I think that works. So if all of these numbers are odd, then their sum is odd because there's an odd number of them. So this is a little bit awkward to write in English, but I'll say oddly many odd numbers. Which such a sum is odd. Okay, let me just give you an example. What do I mean by an oddly many odd numbers? Like if I add up 1 plus 7 plus 5 plus 5 plus 7, right? Maybe that's not the most convincing one because it's got a lot of 7s. Let me add a couple more 7s. Okay, so what do I got here? I've got a total of 1, 2, 3, 4, 5, 6, 7 numbers. The total number of numbers is odd, and every single one of them is odd. That always adds to an odd number. What number does it add to? 28 plus 38, 39. Okay, so convince yourself of that. If you take a bunch of odd numbers, all of them odd, and the total number of them is there are oddly many of them, oddly many terms, the sum is going to be odd. And so that would contradict that they sum to something even. So this is, yeah, proof by contradiction. That's probably the easiest way to think about this. I agree. Everybody okay? Questions about that proof? In fact, let me point something else out that this shows. This is something that our book says explicitly. In fact, this shows more strongly the following. Okay, so this is theorem 711 in the book. Let's call it a corollary. It says, in any graph, when you look at the number of vertices of odd degree, there actually has to be an even number of such vertices. So in every graph, the number of odd degree vertices, that is vertices whose degree is odd, must be even. And I'll let you think about that. Why, again, it follows from the fact that the sum of the vertex degrees has to be an even number. I think, again, if you try to think about proof by contradiction here, if this failed, you would end up contradicting that the sum of the vertex degrees was even. Okay? Any questions about that? I'll let you think about it, why it follows. And you could ask an office hour too if you're completely puzzled. All right, so I want to do some more examples where we're counting in two ways using this principle. And actually, I want to do some more graph theory examples. They're kind of fun. So let me move on to another graph theory counting in two ways thing with vertex degrees. Any questions before we do that? Okay. So let's do some more modeling with graphs and degrees, counting in two ways. This is also going to bring up a class of graphs that we're going to have a lot more to say in the chapter on matching theory. So what's a bipartite graph? This is a very common thing, a bipartite graph. I'm going to lean forward. G. Okay, so again, it's a graph. Again, it's going to be a simple graph. Okay, so there's going to be none of these multiple edges, none of these little loops, not directed. But the vertex set is naturally broken up into two subsets, V1 and V2. So this is, again, this disjoint union symbol. I've got the vertex set broken up into two sets. Let me start drawing one of these. In fact, I haven't finished what the definition of bipartite graph is, but let me draw these bipartite sets in my example. On one side, I'm going to have V1 is 1, 2, 3, 4, 5, these vertices. And V2 on the other side is 6, 7, 8, and 9. Okay, so there's 9 vertices in my vertex set, 1 through 9. And what makes the graph bipartite is that it has every edge going between somebody in V1 to somebody in V2. You never have any edges just among two people in V1 and none among just two people in V2, two vertices in V2. It has every edge. I1, I2, or the two vertices, going between V1 and V2, meaning the I1 is in V1 and I2 is in V2. So let me draw you some edges here. Let's put them in green maybe. I'm gonna have vertex 1 has an edge to 6. Let's say vertex 2 has an edge to 6 and to 8. Vertex 3 has an edge to 6, and that's it. Sorry, I'm looking at my example in my notes. 4 has edges to 6, 8, and 9. 5 has edges to 6 and 9. Okay, so that's my bipartite graph G. Everybody good with this? It's like those matching questions. Yeah, matching theory is about bipartite graphs and picking certain kinds of edge sets in bipartite graphs. And let's actually look at the vertex degrees. In fact, what I want to do is, here, let me write what I'm heading toward. Let's compare the sum of vertex degrees on the two sides. V1 and V2. So what did I do my vertex degrees before we're in pink? So I'm going to draw the degrees in pink. Vertex 1 has degree 1, only one edge coming out. 2 has degree 2, 3 has degree 1, 4 has degree 3, and 5 has degree 2. Everybody see that? And vertex 6 has degree 1, 2, 3, 5, very high degree. Vertex 7 has degree 0. That could happen. 7 was an isolated vertex, right? 8 has degree 2, and 9 has degree 2. Okay. And now I'm going to take the total on both sides. What do I see? 1 plus 2 plus 1 plus 3 plus 2 is 9. And on this side, I see 5 plus 0 plus 2 plus 2 is 9. Iambic. What? You're going to have to explain that one. This is poetry class? You can explain that during the office hour. Okay. So that's the proposition. 9 equals 9, except it's a little more general than 9 equals 9. Let me take it over here again. Make this a little smaller. Okay, so proposition. In any bipartite graph, this happens sorry, G is V comma E, and the V, I have to tell you what the name of the bipartition of the vertices into two disjoint sets is, V1 and V2. Then one always has that if you sum the vertex degrees on the V1 side, you will get the same thing as if you sum the vertex degrees on the V2 side. And actually, there's a nice corollary to this. This is going to somehow be more of the point to the story. Let me give you immediately the corollary, but then we'll prove the proposition. So corollary in particular. What happens if we look at the average degrees on the two sides? So I just mean take the sum of the degrees on one side and divide how many terms there were. Take their average. Their average degrees have this ratio. Okay, so what do I mean? Average degree in V1 divided by average degree in V2. So let's think about that. How do you compute the average degree in V1? What you would do is you'd say 1 over the size of V1, and you'd sum the vertices in V1, take their degree. What would you do to get the average vertex degree in V2? You would take 1 over the size of V2, and you would sum up their vertex degrees. And here's the point, is that these two things, we just decided, didn't mean to do that. Let me circle them both. These two things are the same. That was what the proposition says. Somehow I didn't make that all blue. The blue things are the same number. Good. So we can cancel them. They cancel. This ratio is going to be the size of V2 divided by the size of V1. Everybody see what happened? The denominator here goes in the numerator, and that denominator goes into the denominator. Okay, everybody understand what's going on there? All right. So let's prove the proposition. Does anybody see why the sum of the vertex degrees on the V1 side has to be the same as the sum of the vertex degrees on the V2 side? Any thoughts on that? Wait, let me call on someone. All right. We've heard from you, William. Anybody else have any thoughts? Anybody figure out what these sums are? This 9 and 9, right? We got a 9 here and a 9 here. Anybody see what 9 is counting? Yeah, Theo's saying every line has to connect from somewhere on V1 to somewhere in V2. What is this 9 that they both equal? Someone's saying the half edges. No, but I claim that if you sum up the half edges, you're going to get 2 times 9. Right, edges. Okay, so let's think about that. When you sum over everybody in V1 on the left side, their vertex degree, yeah, you're getting the half edges that come out of the V1 side, but for a bipartite graph, that's the same as the total number of edges. Every edge has exactly 1 half edge on the V1 side. And by the same token, every edge in the middle, right? You pick one of these edges in the middle, like this one, it's got a half edge on the V1 side. It's also got a unique half edge on the V2 side. It's also true that this is equal to this. Okay. That's it. We were just trying to show that these two things were equal. They're both just equal to the total number of edges from counting in 2 ways. Everybody okay with this? Any questions? Okay, so I'm gonna put a little end of proof symbol there. This thing has this corollary that we've put here. All right, and your assignment for next time, before next class, what does this corollary have to do with the New York Times article that's on the syllabus called The Myth, the Math, the Sex? Relate to the corollary. Figure out what that has to do with this. Why does it have anything to do with it?
How do you want us to relate it? Like PDF?
You got to read the article first, Matthew.
No.
Okay. It'll make more sense. So I'm about to turn off the recording unless there's any other questions that we want recorded before we transition to office hour. Any more questions? Anything else I can clarify? Okay. Oh, what is the article again? It's written here in the notes. It's called The Myth, the Math, the Sex. Oh, no, you don't have to. Yeah, just read it. It's linked from the syllabus. You don't have to turn in anything. I just want to make sure you read it. That's all. It's just so we can, talk about it. Nothing to turn in.
I've already read it.
Okay. So I'm turning off the recording now.